Welcome to Dr. BT's Chemistry Essentials, A-Level Chemistry Made Easy. In this video, we're going to be looking at Year 1 acid-base titrations using a known solution to work out an unknown solution. This video involves looking at simpler titration calculations, so those that don't include having to read the level on a burette or work out the mean titer values from concordant results. That will come in the following video. When we carry out a titration, we are reacting equimolar amounts of an acid with an alkali. Either the acid or the alkali is in the burette. Depending on which of these, the acid or the alkali, found in the burette, the opposite is found in the conical flask. Once all the moles of the acid and the alkali are used up, then what we have is neutralization occurring in the conical flask. From an experimental point of view, we can use an indicator that is colour changing in order to observe this. Examples of these are phenolphthalein and methyl orange. And we need something that makes a distinct colour change in order to be really certain of exactly that point, what we call the end point, which signifies neutralisation. The really key thing about being able to use this usefully is this idea of equimolar amounts. We make one of the reactants, either the acid or the alkali, the known reactant, we can work out information surrounding the unknown reactant. For example, if the known reactant is the acid, work out the number of moles of the acid, so we can work out the number of moles of the alkali and use that to work out other useful stuff like the concentration of the alkali, shown in square brackets for concentration. And vice versa. If we know some information about the alkali, work out the number of moles of this, then we can work out some information about the number of moles of the acid and therefore the concentration of the acid. To really understand this, we're going to use an example here of an acid and an alkali reacting together in a quantitative sense. And we're going to make the acid HCl and the alkali sodium hydroxide. The simple equation for this is the formation of NaCl and water. In terms of stoichiometry or molar relationships, you need 1 mole of HCl to react with 1 mole of sodium hydroxide. So it's a 1-to-1 ratio. For this problem, we're going to be looking at the acid, HCl, as our known reactant. So our unknown reactant, the one that we're trying to work out some information about, would therefore, as shown in this relationship here, be the alkali. So in this case, our sodium hydroxide. As both the acid HCl and the alkali sodium hydroxide are solutions, shown by these physical state symbols, then we are going to be quantifying them by using the N equals V times C equation. So there are 3 different quantification terms for each of these reactants. In a titration experiment, for the known reactant, you know 2 of these pieces of information. You know the volume of the known reactant, and you also know the concentration of that known reactant. Concentration is always just given in the actual question stem, or if you're in the lab, it will be given on the label of the standard solution that you're using. Volume of this known reactant is also known because you would have measured this out. If the known reactant is found in the burette, this would be the titer value, and we'll look at that in a minute. Or if it was put in the conical flask, it would be by the volume that you measured using a pipette. The other piece of information that you'll know is the volume of the unknown reactant. Again, depending on where this unknown reactant is found, either in the burette or the conical flask, depends on what value you need to use. So just use this little flow chart to help you work that out. This concludes step 1, is to measure or extract any given information in the lab or in an exam question. Soon we'll come back to how we read off a titer values. This is an important skill both for exam questions and also in the lab. But now, turning our attention to using this information, often questions are going to ask you to work out the concentration of the unknown reactant. So the concentration of sodium hydroxide in our example. It's a common question that is dealing with titrations. However, sometimes you might also be asked just to work out the number of moles of the unknown reactant that's in the solution, so therefore you can work out a mass of it. So just be aware, don't always follow and think you'll always work out concentration. Work out what the question's asking you. So if we want to get to this point, we need to, first of all, get two pieces of information to get this third, because our equation of 3 terms requires 2 to find the third. Now we can't do this with the unknown reactant, but we can use some information of the HCl, our known reactant here, as we have 2 pieces of information. So with volume and concentration, we can work out the number of moles of the HCl. Having calculated the number of moles of the known reactant, we then use the molar ratio of the known to the unknown, so here it would be 1 to 1, to work out the number of moles of the unknown reactant. Now have 2 pieces of information for the unknown reactant. We have the number of moles and its volume. So we can calculate the concentration of the unknown reactant by rearranging N equals V times C for the unknown reactant. So at the moment, this is a bit of a simplification, but it's giving you an overview of how you can use the relationship in the equation in order to work out a concentration. We're going to apply this model to an actual question now, and we're going to have to add in a few more steps as we deal with actual real data. So what I would like you to do is to read through this exam question, and then we're going to look at how to approach a titration question. Okay, so first of all, we need to box the value we're trying to calculate and underline any given values. So we can see here we're trying to work out the concentration of sodium hydroxide, so that's the B of our bug. We're boxing the thing we're trying to work out. And then our underlying values, the UG of our bug acronym, are as follows. The second step is to write the equations, and in terms of a titration question, this is a strategy using the equations. As part of this strategy, we need to identify the known reactant and the unknown reactant. Now, the unknown reactant is always going to be the one that you're trying to work out. It also only one piece of information given. As you can see here, the one piece of information is just the volume of the sodium hydroxide. So we've identified both of the reactants involved. Now the third step is then to check any units of any given values. In this case, because we're using the MVC equation and concentration is always in moles per decimeter cube, then any centimeters cubed need to be converted to decimeters cubed. This by dividing by 1,000. Generically, our fourth step is to rearrange the equation, but with this strategy, we have to look at it differently. We have to think of our rearranged equation as coming into play later. What we're going to do is fill out our strategy grid. First, by substituting in the values, and then do our rearranging as part of this. So, we're going to take our known information. Then we're going to use these steps here that we looked at in the previous slide to work out our concentration, our final goal. So we need to calculate the number of moles of the known, and that N is going to be volume times concentration. So we take our values. In our calculator, we work out that we have 0.00402 moles. And not to do any rounding up until the very last stage, because otherwise you are just creating problems with yourself with sources of inaccuracy. Then what we need to do is use the molar ratio to calculate the number of moles of the unknown reactant, sodium hydroxide. Now in this question, they've not given you a balanced equation, so you'd have to construct that. The result that's formed is sodium chloride and water, and that is balanced as it is. So we can see the molar ratio between the reactants is 1 to 1. We can fit our molar ratios up here. Again, this step is just to formalize this process. If you can do it without putting that particular row in, then go for it. But what we need to know is that going between here and here, we just literally keep it the same. We times by 1. Do exactly the same operation to our number of moles. And now, having got that, we can calculate the concentration of the unknown, our final goal. using a rearranged version of this equation. So making concentration the term, that's number of moles divided by volume. Volume's in decimeter cubed, so all's good. And in the calculator, that gives us the following answer, which to the appropriate number of significant figures, which is the unit of any given values, of which has the least significant figures, which is our 25 centimeter cubed here, as that's 2 significant figures, is 0.16. See how this approach here, with a bit of a modification of not having to rearrange the equation because you've already got strategy outlined, gives you the concentration of an unknown reactant. So just to summarize everything so far, because there's lots going on here, this is our steps to tackle a titration calculation. So we box and underline any given values, box what we need. These little green ticks here are the given values that we're given. That then allows us to start to form this column here. The known reactant we identify as having 2 ticks. The unknown reactant as only 1 tick, so 1 piece of information. Convert any units of any given values, and this is volume of interest, so centimeter cubed into decimeters cubed, so that it matches concentration, and that's because this equation requires decimeter cubed. Now, also the volumes themselves can be measured in the lab, and it depends on if they're in the burette or the conical flask, so this just little summary allows you to work that out. Concentration will always be given in the question, or if you're in the lab, as a label on the standard solution. Then what you do is you substitute in the values that you're given or you're measured into these 3 areas here. Then you use this grid here to calculate the concentration of the unknown. So you calculate the moles of the known by using this equation. So the volume and concentration on this side gives you the number of moles here. Then you look at the molar ratio in the balanced equation to then get the number of moles of the unknown. And then with that piece of information and the volume that you've got at the very beginning, when you underline those given values, you can work out the unknown concentration. So this is useful. I would get it down in your notes as sort of a crib sheet on how to tackle these types of questions. So pause the video here and do that if you'd like. What I'd like you to do now is read through this question, pause the video and have a go at this. Okay, if your answer for the concentration potassium hydroxide was 0.135 moles per decimeter cubed, then you've got the correct strategy. If you haven't got that, I'm going to quickly go through the walkthrough of this. Boxed and underline any given values. Then we need to put our equation down, and it forms this grid. Doing this, we can start to see which one is the unknown, because that's the one we're trying to work out. So we've got potassium hydroxide here, and then we're going to label up as the known one, where we've got 2 pieces of information, the concentration and the volume, as HCl. Let's convert units of any given values. Our volumes are in centimeter cubed, and they do not match the volumes in the concentration, so we're just going to have to change them. It's decimeter cubed by divided by 1,000. Then what we need to do is substitute in these values. Remember, we don't need to rearrange because we're going to use the grid to allow us to do that. We need to calculate, and we know that there's 3 steps to this. Step is the known, so number of moles of the known HCl is volume times concentration. Then what we need to do is work out the number of moles of the unknown. Do this by looking at the symbol equation and the mole ratios. Well, it's 1 mole of potassium hydroxide to 1 mole of HCl. Relationship of 1 to 1 means that the number of moles of the unknown is also 0.00135 that reacts with the acid on neutralization during the titration. Finally, we now have 2 pieces of information in our column for the unknown potassium hydroxide, so we can work out the final thing, which is concentration of potassium hydroxide, and C is equivalent to moles over volume. So we put that into the calculator and we get the answer 135, and then we check the units, and that's obviously moles per decimeter cubed as it's a concentration. Okay, final little practice at this round is to have a go at this question here. So pause the video and have a go. Okay, if your answer was 0.035 moles per decimeter cubed, then you've got the right answer. If not, don't worry, we're going to quickly go through it. First of all, we boxed the value we're trying to calculate and underlined any given values. Next thing we're going to do is get our equation, which in this case is our titration grid. We've identified that obviously we're trying to work out the concentration of sulfuric acid, so that's our unknown, and our known is going to be the sodium hydroxide, NaOH. Step is then to convert any units. So we've got centimeter cubed here, so we're going to have to convert it to decimeter cubed so that we get it in the correct form for the volume. This in, we don't need to rearrange because we've got our grid, so then we substitute in our values. With this, we can start to calculate it. So obviously we've got V and C here, so we can work out N by doing these two multiplied, volume times concentration. We've worked out we have that many moles of sodium hydroxide. Then what we need to do is look at the mole ratio. Now we need a balanced equation for this. So the sodium hydroxide reacts with the sulfuric acid to form sodium sulfate. And obviously you need to be really, really careful at A-level that you have that absolute nailed, that you can work out the formula of a salt. Obviously SO4 is 2 minus, each Na is plus, so we need 2 lots of them. And then we also form water. This isn't balanced because obviously we've got 2 sodiums on this side and only 1 on this side. So if we just correct that, we have a 2 there. So we have 2 waters. Now balanced, it also highlights the molar ratio of the acid to the alkali. So it's a 2:1 ratio. So our mole ratio on here is our sodium hydroxide is 2 and 1 for sulfuric acid. So obviously to go between these two numbers, you'd have to divide by 2. Do the same operation to the moles. This is that value. Then we're left to work out concentration. Concentration is rearranged from the equation N equals V times C. So to make C the term, we've got to do N over V. And then we just substitute in those values. That then gives that value. And then we just take it to 3 significant figures, as this is the appropriate significant figures for all of the information we're given, as that's the lowest significant figures there, gives us our answer. Okay, hopefully you found this video as an introduction to titrations useful. If you have, ensure that you like the video and then ensure that you subscribe to the channel for new videos as and when they're uploaded. The next video on titrations will involve looking at being able to read a burette, working out the mean titra, and then some more complicated titration calculations.